Right, continuing on with the law of sines and into word problems. Problems 2 through 5 will each be a word problem application of the law of sines. So problem 3 states that the Federal Communications Commission is attempting to locate an illegal radio station. So it sets up two monitoring stations, alpha and beta, which I just labeled as A and B in the triangle below. And it tells us that station beta is 38 miles due east of station alpha. Alpha measures the illegal signal from a direction of 43 degrees east of north, whereas station beta measures the illegal signals coming from a point that is 32 degrees west of north. How far is the illegal signal from monitoring station alpha? So to put that in context of the triangle that's drawn below, we should probably label a few things. We know that that first bearing angle was 43 degrees to the northeast. We should have a 43-degree angle there. That second angle we know to be a 32-degree angle to the northwest, giving us that red angle over on the right. And the thing that we're solving for is the distance from station alpha to the illegal radio signal, which means we're actually going to be looking for side length B, which will be this one over here. Now I just drew a ray from each of points A and B in the directions indicated. So it must be that their intersection point is where that illegal radio station is coming from. So I'll label that point C since it's just the one that we're missing. So now I have my triangle ABC, and I should start working to get as many pieces of that triangle as I can. So each of those bearing angles that we had, since they always have to be measured from the north or south line, means that we actually have an angle exterior to the triangle rather than the triangle's interior angles. So I'm going to start by figuring out what those are. So over in the left corner, the actual measure of angle A is not going to be 43 degrees, but instead be 47 degrees, since it should be the complement of 43. It's like the measure of angle B should be the complement of 32 degrees, which works out to 58 degrees. And we'll use that information to get our missing angle C, which should be 180 minus 47 minus 58. And that comes out to 75 degrees. Go ahead and label that angle. So now I've got all three angles that are inside of my triangle, and I know one of the side lengths, so I can use the law of sines to find any other side that I need. And again, we said that we'd be looking for the length of B, so we'll have B over the sine of 58 degrees is equal to 38 over the sine of 75 degrees. Solving that for B, we get 38 times the sine of 58 degrees divided by the sine of 75 degrees, which works out to 33.4 after rounding to the 10th place. And since our initial distance, which was 38 miles, is given in miles, then this distance should also be in miles. Okay, in problem 4, we're told that redwood trees in California's Redwood National Park are hundreds of feet tall. Notice that extra beautifully drawn tree in the diagram below. A sighting to the top of one of these trees is taken X feet away from the tree's base at an angle of elevation of 44 degrees. You then go another 100 feet away and take another sighting at an angle of elevation of 37.2 degrees. Our goal is to find the height of the tree. Start labeling the pieces that we know. That first angle of elevation we were told was 44 degrees, which would be that angle labeled in blue. The next angle of elevation we're told is the one that's 100 feet away at this 37.2 degree angle. And we're going to ultimately be trying to solve for the height of the tree, which I'll mark NH over there inside that tree. So it'll probably be helpful to give some labels to our triangles so far. Well, let's label this line C, which is going to make this angle over here C. If we label this side A, that'll make this first angle A, leaving only B for the final option, which I'll mark over here. And we already know the length of B, it's 100 feet. So if I were interested in solving for H, the thing that I would probably want to notice is that I have a right triangle that contains H already. That being this triangle shown here. This is a right triangle. It's got a 44-degree angle in the lower left corner. Its opposite side is H, and its hypotenuse is C, while its adjacent side is X. So that right triangle would be nice to work with if I knew any of the side lengths in that triangle. Fortunately, I don't know any of those yet, but I can still set up an equation that deals with H and that 44-degree angle. So let's use sine so that we have opposite over hypotenuse. I can say that the sine of 44 degrees is equal to H divided by C for opposite over hypotenuse, where H is for height and C is going to be the hypotenuse. So if I knew the length of C, then I could solve for the height. So that's going to become our new mission, is first find the length of C, and then I can substitute it into this equation to find the length of H. So let's go about doing that. Means the next thing that we're going to want to do is identify as many angles inside of that, inside of our extra triangle that's sort of there to the left of the right triangle, the one that's a non-right triangle, and is also pretty skinny since it was drawn to scale. So just going to move this label outside, and we're going to label this interior angle right here. That'll be angle A. So A is the angle that's inside of that oblique triangle. Sometimes I'll say other triangle, and I really mean the oblique triangle, which again just means a non-right triangle. Enough semantics. I know that angle A should be the supplement of 44 degrees, so it's 136 degrees. Lastly, I should get the measure of angle B, which should be 180 degrees minus 37.2 degrees minus 136 degrees. And that comes out to a very small angle. It's just 6.8 degrees. We'll come down and label that about here, 6.8 degrees. Right, and now we'll use what we know in order to get the measure of length C. So from the law of sines, I should get that C divided by the sine of 37.2 degrees is equal to 100 feet divided by the sine of angle B, which would be 6.8 degrees. So that gives us that C is equal to 100 times the sine of 37.2 degrees divided by the sine of 6.8 degrees. And then I will take that value for C and substitute it into the equation that we had earlier for H. So that H should be 100 times the sine of 37.2 degrees divided by the sine of 6.8 degrees. And then all of that should be multiplied by the sine of 44 degrees. Doing so means that this height comes out to 354.7. And we were measuring in feet. Right, and finally, problem 5. We have that the finish line for a race is 3 kilometers due north of the starting line. A runner begins the race by running at an angle that is 25 degrees east of north until she reaches a resting point. She then finishes the race by running an angle that is 70 degrees west of south until she reaches that finish line. How far did the runner run? So let's start by labeling some of the stuff that we know. Our first bearing angle from the start line should be 25 degrees east of north. So we'll measure this angle to be 25 degrees. Next, she'll get to the stopping point, at which point she'll then go in a direction that is 70 degrees west of south, which means we're looking at this large angle marked in red to be 70 degrees. And then we'll end up at the finish line. Also, we marked that that finish line was 3 kilometers due north of the starting line, and that Rainbow Road is the runner's path. So now we want to take what we got in the given information and start putting that in context of this oblique triangle that we want to work with. Since at the moment, we only have one interior angle so far. So one thing we're going to use to our advantage is that the bearing angle to one location is the same bearing angle from that location back to the origin point, just with a different cardinal direction. So what that means is that while the second angle marked in red is 70 degrees to the southwest, that means if I measured from the finish line, I should have a 70-degree angle to the northeast if I wanted to backtrack. Same thing with our other bearing angle. Since it was 25 degrees to the northeast, to get to that stopping point, that means if I was at the stopping point, I could go 25 degrees to the southwest to end up back at my starting line. So we're going to use those new angles in order to find the last two interior angles of our triangle. By the finish line, This angle that is on the inside of our triangle should be the supplement to 70 degrees. So it's 110 degrees. And the upper right interior angle should be the difference between our two bearing angles. So the difference between 70 degrees and 25 degrees. So this interior angle marked in green should come out to 45 degrees. And you could also check again and find that 25 plus 45 plus 110 will be equal to 180. So it'll satisfy that as well. And then let's talk about what we're actually trying to find. We want the total distance that this runner runs. So rather than finding just a single side to this triangle, I'm actually going to want to find both of the missing sides and add them together, since the total distance the runner runs should be this first line, which I'm going to call A, plus the second line, which I'm going to call B. Just because that'll be her path, A and then B. Which means that I'm going to want to use the law of sines to find both of those. So we'll start with A, because it's first in the alphabet. So A divided by the sine of its interior angle, which is 110 degrees, is equal to 3 divided by the sine of its interior and corresponding angle, which is 45 degrees. So A works out to 3 times the sine of 110 over the sine of 45. 110, 45 degrees. Punching that into a calculator, you should come up with 3.99. Since A is just an intermediate answer, I'm going to round to a couple of extra decimal places so that I can make sure that my final answer is the most accurate. Now I'll do the same thing to get B. So B divided by the sine of its interior angle, which is 25 degrees, is equal to that same thing on the other side, 3 over sine 45, meaning that B is 3 times the sine of 25 divided by the sine of 45. 25 degrees there, 45 degrees there. Plugging that into a calculator, I got 1.79. And finally, that total distance, which I'll mark in purple, since if I add blue and red together, I get purple. You know, why not? That distance should be the sum of A and B. So A plus B, which is 3.99 plus 1.79. And if we add blue and red together, we get purple. So 4.8, because I'll round that to the nearest tenth, since that's what the problem was asking us for. And all of our distances were measured in kilometers. So it should be kilometers.